Okay, we'll continue with the next module. So far we've talked about vectors and matrices, right? Uh, this module will kind of look at an application of where these ideas are useful. So this is on module on well, linear equations and their solution. Right? We won't see how to solve them, but we'll only look at the nature of their solutions and what that means and all that. We've studied linear equations since our high school. So a set of simultaneous linear equations look something like this. And say one equal to let's say okay, where x1, x2, xq are the unknowns. Okay, this is one equation. And then similarly you have let's say p equations. Okay. A set of simultaneous linear equations is essentially a set of equations like this with q unknowns, where the x1 to xq are the unknown variables. Whoops. And the other set of parameters aij and bj are all known variables. Aij's, the coefficients of the equations. Okay. So this set of equations, we've learned about matrices and n vectors. So it turns out that this can be very compactly expressed like this. Okay. Which essentially means, well, we have to first talk about what are the sizes of these. If we were to express uh, a set of p equations in terms of q unknowns like this, where the vector x is a column of your unknowns, x1, x2, xq, and b is essentially the right hand side of this equation, b1, b2. It's a p vector. What will this be? What will be the size of a? And what will be the elements of a? Sorry, what will be the size of a? How many rows? How many columns? P cross Q, yes. Okay, what will be the first element? It will be A11, A12, A1Q, A21, 22, A21Q, AP1, AP2. Okay. Okay, for now we'll assume all of them are real numbers. A, B, and the solution also will in fact be a real number. So this now is a vector from P, Q, and this is okay. So one of the uses of using the matrix notation is something uh, elaborate like this can be very succinctly expressed in this form. Okay, you don't have to write this every time. You can simply write it like this, and then you know what this you. Once you see this, you know you're talking about a set of bunch of simultaneous linear equations, and which can once you know A and B, you know exactly what those equations are. It turns out that Ax equals to B is actually is something that we come across in science and engineering a lot. So this is actually very useful. Because this we come across equations of this form very regularly. Okay, and there are two ways to look at this. So in this case, right? So what we're trying to say is, okay, we have uh, a bunch of equations like this, and there is usually a set of unknowns that we don't know. All we know is that those unknowns satisfy this equation, and our goal is often to find out what that unknown is. Okay, the kind of problem we often come across in engineering of this form are of two types. One is called a control problem. Estimation problem. See, both of them, mathematically, both of them are just a process of solving this. Okay, uh, it's the difference between the two is essentially the interpretation that we're giving for this set of equations, which is essentially application dependent. What you're looking at in control problems, so your A, X, and B uh, would have slightly different terminology. Would have different names for them. Okay, in a control problem, you're dealing with system that has some input and that has some output. Okay, you have control over the inputs. Okay, and it produces some output. Okay, and here your input is essentially X. Okay, that's your input. Your output is B. And this matrix A is essentially what relates the input to the output. Okay, so this is often called the system matrix, or something that relates or tells you how the output of the system are related to its input. Okay? So if that is the case, right? Uh, if X equals B, okay, and if X is the input, B is the output of the system, and this is essentially the physics of the system. How does the system? What does the system really do? Then, what would be our interpretation of this individual number in this matrix A? What would this number tell me in the context of a control problem? Yeah. So it's some number, right? Let's say the number is 5. What does that really tell me? Or how can I interpret this in the context of the relationship between the input and the output? Sure. Exactly? Good. What input and what output? Well, the clue really is ij. Can you tell me what input and what output based on the indices that I've given here? Position. Well, what do I and j represent in the matrix? Row and column number. Row number, column number. From this, can you tell me one way of interpreting aij? Well, there are p equations. Okay, this will appear only in one equation, right? Which equation would it be? There are p equations here. Aij appears only in one equation. Which of those equations is it? Ith equation, right? So that means this appears only in the ith equation. Okay, what does the ith equation really tell me? Bi. So what is that? What is Bi? That's the ith output, right? So ith equation that corresponds to the ith output. So that one thing is clear. This tells me something about the ith output only. Okay, so that we've sorted that out. What about j? Yes, the j essentially tells you this is input. So now can you tell me what is the interpretation of this? What does Aij really tell me? Okay, let's take a simpler system, right? Two inputs, two outputs. What does A22 tell me? A22 tells me how the second input affects the second output. Okay? Like here, how the jth input affects the ith output. Okay? So this number itself tells me how sensitive my the output of my system, a specific output of my system, essentially the ith output, is to the jth input. If this number is very large, that means if I change my jth input slightly, the corresponding output, ith output, is going to change by a large amount. If it's a positive amount, if let's say if it's a positive number, a small increase in the jth input will lead to a large increase in the ith output. If it's negative, then a large increase in my jth input will lead to, sorry, a small increase in my jth input will lead to a large reduction in my ith output. Clear? What if it was 0? What would that mean? Which input? See, you cannot just say input anymore because there are how many? There are Q inputs and P outputs. So which input? No. Here. Okay. See, the input, right, is something you can choose, right? That's under your control. Output is what you measure. Aij is simply the nature of the system. Okay. So if Aij is 0, that simply means that the jth input has no impact on the ith output. Okay. Similarly, if I make A22 0, right, then B2 is simply A21 x1. It doesn't matter what the value of x2 is. Right? X2 does not affect my second output. Okay. Right. So from now on, whenever you see matrix like this, a matrix, and you have a bunch of elements, one way to think about it is of each element is it tells you how the jth element here affects the ith element here. Okay. So now, in the context of a control problem like this, what we are interested in is we often want the output of the system to be in a particular form, okay, or a particular value. Okay. So this often is something that we want, or a desired. We want a desired value for B because we want the output of the system to be in a particular, to have a set of values, right? Let's assume we know the physics of the system, how the system operates. Okay, so we know A. And often the question is, okay, how do I select my inputs to the system so that I get the output that I want? Okay, so that's the kind of problems that we deal with when we're dealing with control problems, where you have complete control over X that over X, the inputs that go to the system, and often you're interested in a specific output that you want from the system. You know how the system operates. That means you know A, and then the applications or places where we come across equations like this is essentially this problem. Physics of the system is known. You know what the desired output is, and you want to choose the input so that you get the desired output. And this applies only for systems like this, which are linear systems. If the relationship was nonlinear, then of course you cannot use this. See, one way to think about this is this. Okay, let's assume a particular patient can be reasonably or the physiology of a particular person is reasonably approximated as a linear system in the range of in the region where let's say the body is operating, and let's say we know that A, right, and B is, let's say, a bunch of clinical measurements of interest, maybe blood glucose level, maybe resting heart rate, maybe the LDL levels in the blood, and so on and so forth. So there is a bunch of measurements that we have, and X could simply be set of clinical interventions or behavioral interventions that you have control over. You can give a specific medication. You can tell them, let's take a walk every day for 20 minutes, things like that. This we have control over. And if this particular pathophysiological problem that the patient has can be modeled, can be reasonably modeled by as a linear system like this, where your interventions that you're giving, clinical or behavioral, relates to the output measurements or the output clinical measurements that you're interested in through A, then you can use Ax equal to B to solve for what interventions you should be giving to get the patient in a healthy state that you're interested in. Okay, that's one place where you come across something like this. And if you remember in the first lecture, we looked at an example where often, even if you have a highly nonlinear system, okay, there might be cases where a linear equation like this might still be useful. For example, if you remember this, this is let's say let's say top view of your arm. This is your shoulder. This is your elbow. Okay? And this is your hand. Right. This is your shoulder angle. I call theta 1, theta 2. The relationship between theta 1 and theta 2 and endpoint position xy. Let's say this is your origin. This is x. This is y. The position of the hand and its relationship to your shoulder angle and elbow angle is nonlinear. If you can find out what x and y are in terms of theta 1, theta 2 by doing simple trigonometry. That relationship is nonlinear. So if this x, y is some nonlinear function of theta 1, theta 2. Okay. This does not fit this picture, ax equals b. But it turns out if you take the time derivative of the left-hand side and the time derivative of the right-hand side, if you take the time derivative on the left-hand side, the derivative of a function or a vector is simply the derivative of the individual elements. Okay. The derivative of the first element and the second element will simply give you the velocity of the hand and its components along the x and y direction. Okay. So this will be Vx, this will be Vy. It turns out that once you take the derivative on both sides, you'll get an expression like this. This is a 2 cross 1 vector, 2 cross 1 vector. And this will simply be a 2 cross 2 matrix. Okay. There will be a linear relationship for a given value of theta 1 and theta 2. Don't worry about what that means, right? Okay. But it turns out that the kinematics of this two-link arm, even though the position kinematics is nonlinear, the velocity kinematics will have a linear relationship. That means there is a linear relationship between the angular velocities of shoulder and the elbow to the endpoint velocity of my hand. Okay, so let's say I know J, and let's say I need to move from this point to this target location. Okay, if I have to move to that target location, I know the direction in which I have to move. Right, and let's say I need to get from this point to this point in 1 second. Okay, then you decide, okay, I'm going to move at a constant speed, and that speed depends on how long, or how large this distance is, and how much time do I have. Okay, and the arrow connecting these two tells you the direction in which you have to move. That means you know this. This is something you want. I want to move from this point to this point with some velocity. Okay? So if you know J, then you can solve for this, assuming that J has the property so that you can solve this equation. You can solve for theta 1 and theta 2, essentially to say how much do I have to move my shoulder, and how much, at what velocity should I have move my shoulder, and what velocity should I move my elbow to be able to move from this point to this point at a constant velocity. Right? So even though our original problem was nonlinear, in this particular case, x equals to b still applies because a modified version of this problem is linear. Okay, so this would be another example of a control problem. So the estimation problem, on the other hand, it's the same equation. The only difference is x is again an unknown, and x is not something you have control over. Okay, you have no control, and there is no way to directly measure. There is no way to directly measure it. Okay? And the interpretation here is like this. Let's say you have some system, right? Okay? And all you can do is make some measurements from the system. Okay? And we'll call those measurements B. Okay? The measurements that you get out is determined by some properties of the system, right? And those properties, let's say we can represent those properties through this uh, parameter vector x, something that is inherent to the system. Okay, and it's these parameters of the system that actually give me my measurements. Okay, and how these parameters x are related to to the measurements that I make is given by the matrix A. So in this case, so here in the control case, this is output, input, and this is system dynamics. Here B is your B represents your measurements. X represents your system parameters. A is your, the different names. This could be a measurement matrix. Or okay, the primary difference is here you were interested in solving with something that you could control so that you could get the desired value B. Here you've made a bunch of measurements, and from that you're asking, okay, what are the properties of the system which are represented by X? Okay, given that I've obtained these measurements and that I know how these properties affect my my measurements B. Similarly, just in the case of control problems, what would this particular coefficient in my matrix tell me? What would be the interpretation of this coefficient, Aij? Well, Aij appears only in the ith row, ith equation. That means it has to do something with the ith measurement, right? Because B's are your bunch of measurements. So this tells me about my ith measurement. And what does the J tell me? Well, not input in this case. Let's say J parameter. This tells me how my ith measurement is influenced by the J parameter. Okay. All right. See, one nice example of an estimation problem, which we will study in a little bit more detail later on in the course, is the problem of CT stands for. Do you remember what does CT stand for? Yes. Computer tomography. Okay. Say this is some object. Okay. And I'm interested in, say, measuring the distribution of the density of the object on the inside. Okay. I want to know what is the density of this object at each point inside the body. Okay. Turns out one way to measure this is you take a bunch of X-ray sources, okay, and then you simply shoot X-rays from your sources, and you put a detector on the other end. Okay. You shoot a bunch of X-ray sources with fixed. You fix the intensity and you fix the number of these sources and number of these detectors. Okay. And if you shoot X-rays through this body, it turns out X-rays will simply pass through the body in a straight line while undergoing some level of attenuation. And the amount of attenuation that the X-ray undergoes essentially depends on the density of the body inside here. Okay, that means the measurement that I get from this detector, okay, depends on the path taken by this ray, depends on the original intensity of the ray that started from here. It depends on this path that was taken, and the density of the body along this path. Okay. Now let's say I have the ability to now rotate the detector and the source and keep them in multiple orientations. So I do one here, one like this, like this. Let's say I rotate it around and I take, essentially I shoot X-rays and then I take a picture, snapshot of the X-rays the attenuated X-rays that come out using my detector. Right? Here, and these are essentially fixed. Okay. The outputs of your detectors, right, at these different angles, those would be the measurements that you've obtained. Okay. And because we want to do this numerically, what we would do is, of course, we can't obtain the map of the continuous distribution of its density. We will divide the body into discrete segments like this and make the assumption that within a pixel or within a segment, the density of the body is constant. If you make this assumption, right, or if you model it like this, it turns out that the measurements that you will get will be related to the vector of densities in your body. Now, imagine now let me draw it here. Say you have the body and you divided the body like this. Okay. And you're calling this the density of this first pixel as x1, this is x2, x3, x4, x5, and so on and so forth. Okay. Those are your unknowns because what you're interested in is the density, right? In the CT reconstruction problem, it turns out that the measurement that you take is actually linearly related to your x's. Okay. Right? And the linear relationship is given by matrix A that depends on a few things. Depends on, of course, it depends on the original intensity of the X-ray that you shot from your detector, and it depends on the geometry of your source and detectors that you used. For example, I've drawn a bunch of sources and detectors where the X-rays are shot as parallel rays. You could have a situation where you have a body and you have a source here, a detector here, and it's shooting X-rays like this, okay, or some other arrangement. Okay, and see here I've drawn it as if I'm rotating the source and the detector 360 degrees. Some of them might not do 360 degrees. They might only do, let's say, 180 degrees. Right? All that is encapsulated here. That is captured here. Right? So for a given CT system and a given geometric arrangement of your CT machine and the protocol that you follow for taking your making your measurements. That is all here. So you'll have to derive the expression uh, for each case, depending on what kind of system you've developed, and then come up with A. B, anyway you measure, it's given by your detectors. This is given by the design of your system. And it turns out that this problem is actually very well, it is linear. And if you discretize it like this, then you can express the problem of identifying the density distribution within the body as a linear problem X. And here, the parameters of the system that we're interested in, something internal to the system, are these density values. Okay, so these are the two types of problems where X equals to B comes up. And now we will go about understanding whether or not, or understanding the nature of the solutions of X equal to B, to really know, can we really solve this? And if it, when is it that we can solve it, when we cannot solve it? And if we solve, is there only one solution, or are there four solutions, or there are infinitely many solutions? Again, as usual, that like we do in the course, we always associate most of the ideas with geometry so that we can visualize stuff in our head. See, when we studied this in school, let's say we write a simple example first. If you are given a set of equations like this, you know how to exactly solve this, right? But there was a geometric picture associated with this set of two equations, right? What is the typical geometry associated with these two? The one that we're used to from high school. What does each of these equations represent? What does the first equation represent? In a plane. Yeah. Yeah, 2D plane. What does the first equation represent? Represents a line, no? Each of these equations represents a line. If you're talking about a problem in R2, okay, two unknowns, then each of these equations represents a line, right? So I don't know what this is. This is maybe this. This is this. This is line 1. This is line 2. Let's say this is. So if you algebraically solve this, you get a set of numbers x1, x2. Geometrically, what that means is the first equation is represented by this line. Second equation is represented by this line. And when you say you're solving this, that means you're looking for a point in R2 such that both these equations are satisfied by that point. That means the point lies both in L1 and L2. Okay, there is only one point like this, at least in this case. So if you solve for this, that will exactly correspond to this. Okay, if you solve for this, what do you get? You get x1 equals 3, and is that correct? No, x1 equals minus 3, and this is that will essentially be, well, I've not drawn it correctly, but yes, the point will be this. This is the view that we are used to. Okay, what if you had three equations and three unknowns? What would be the picture then? What does each equation represent if you have three equations and three unknowns? You're now dealing with a problem in R3, and there each equation is supposed to represent what? A plane. Okay, and when you say you're solving these three equations, you're essentially saying at what point do these three planes intersect? Okay, okay, two lines can intersect at a point. Three planes in 3D can intersect at a point, right? Now, if you go to higher dimensions, if you have A, which is, let's say, R P cross P, that means P equations and P unknowns, each equation essentially represents a hyperplane in RP. Okay, the intersection of and the dimension of that plane itself is p minus 1. So when you say you're solving Ax equals b, where A is p cross p, you're essentially asking there are these p minus 1 dimensional planes in RP, and the intersection of all those p minus 1 planes is the solution to your equation Ax equals b. Okay, and this way of viewing each equation with a geometric entity is called the row view, because you're associating a geometric entity with each of the rows. Okay, this we are used to. Okay. And at least in R2, this view is very useful, because if I give you these equations uh, and I give you the lines, you can already tell me whether or not that system has a solution or not. Okay. So using just the geometry, when would you say a system of two equations with two unknowns does not have a solution? What does it mean to say does not have a solution? Sorry? Right. So if the two lines were parallel to each other, when I say no solution, right, that means there is no point which simultaneously satisfies both equation 1 and equation 2, which lies both on line 1 and line 2. If they are parallel, there is no point that lies simultaneously on both. Whereas here, if they are not parallel, they are bound to intersect at some point. Okay, so this is the case of unique solution. This is the solution. Are those the only two possibilities? Is there some other possibility? Can you have two solutions? Well, with straight lines, you cannot. Okay, can you have infinitely many solutions? No. See, these equations are only straight lines, so curved lines are not allowed, because we've restricted ourselves to the study of simultaneous linear equations. Linear equations of this form are always flat geometric entities. Like in 2D, it's a line. Well, straight line. What if both the lines were the same? L1, L2, right? For example, x1 plus x2 equals 1, 2x1 plus 2x2 equals 2. Both of them are exactly the same equation. That means all the points on this line will solve this system of equations. So in 2D, there is this nice geometric picture that we see for when there is a unique solution, no solution, or infinitely many solutions. It just turns out that this picture is not very good the moment you move to higher dimensions. In fact, the moment you move to 3D, there are many different possibilities where there is no solution, because there are many possible cases where how the planes intersect. Okay, and you can have no solution, right? So this row view is not really that useful when you go when you go beyond R2, it gets too complicated. The other view, which is actually very nice and useful, is the column view. And for this, we now have to go back to our the things that we've studied in our in the first module and the second module, right? So we know we can express a set of simultaneous linear equations like this, right? Let's again take this example. X1 plus x2 equals 4, 2x1 plus x2 1. Okay. Can you tell me what A, X, and B are? If these are the equations, what is A? X is easy. X is simply x1, x2. What is B? Yeah, what is A? You'll have to be louder. Yeah, 1, 1. That's all. This is okay. All right. So if you multiply this out, you will get these two are the same. In the last module on matrices, we saw the example of, or we talked about the interpretation of something like this. Post multiplying a matrix by a column vector. What is the interpretation of this? What operation am I doing when I do this? Yes? No, not linear equation. A. Right, you're taking the columns of A. What are you doing to the columns of A? Yes. So essentially, you're taking the linear combination of, right? If that is the case, can you describe in words what this equation is saying? Don't say, oh, A matrix A multiplied by vector x gives me B. Using this interpretation of AX, what does the left hand side and right hand side tell me? This equation. X equals B simply tells me this. And let's say I want to solve for this. Okay. When you say X equals B, you're saying some linear combination of the columns of A gives me B. Okay. And you're asking, what is that exact linear combination? What are the coefficients of the linear combination? Right? If you were to rewrite this, right? If you were to write the left hand side as a linear combination of columns of A, how would I write this? So you take the first column multiplied by x1 multiplied by x2 x1 and x2 tell me what specific linear combination I'm supposed to take. Okay, and this equation tells me that that linear combination is equal to 4, 1. Okay, and if you're trying to solve this, then your goal is to find x1 and x2 such that the linear combination of the columns of A gives me B. Okay, you can verify this. This is exactly the same. Again, you should at this point already know what this means, and that you know that that gives you this. Okay. See, if this is the case, we can associate a geometry with this, right? Now, this is R2. Okay. This is your B, right? 4, 1. Okay. And there are two other vectors here, the columns of A. A1, I'm going to write it like this is the first column of A, second column of A. The first column of A is 1, 2. That means 1 here. This is A1. This is A1. A2. This is here. Now, all you're asking is this. How do I scale A1 and A2 and add them together so that I get B? Okay, that's the column view. That's the geometric interpretation of this equation, which we call the column view. Okay. Now, essentially, you have to scale A2, A1, and then the sum of those two should give you this. Okay. See, I know I'm adding two vectors, scaled versions of A1 and A2. That means it's a parallelogram. I apply the parallelogram law of addition of vectors. And I know the sides of the parallelogram have to be parallel to this line and this line. Right? So now, if I take this line and uh, I draw a line from the tip of B parallel to A1, right? So that would be, so, I mean, I've not drawn it properly, but it'll meet somewhere here, and the other one will be somewhere here, and then what you'll end up having, what is the solution? -3 and 7, right? Is that right? Yeah, -3 and 7. So so what that means, so if you take -3 times A1, that means you flip A1 and then you take -3 times that. You take 7 times A2, and if you add them together, you'll get B. Okay, that's the geometry of the column. Right now, the advantage of this, right? Now, if you move to 3D, right? If you have 3 equations and 3 unknowns, you're asking the same question. I have 3 columns of A in 3D, and then I have my B that is pointing in some direction. How do I scale A1, A2, A3, and then add them together so that I get B? This view applies to any Rn. Okay, but what we'll have to see now is the 3 possibilities: unique, no solution, and infinitely many solutions. What would they correspond to in this particular view, which we will come to a little later? Okay, is it clear? Is the column view clear? Okay. Okay. We'll now move on to looking at the. Okay. See, there are only 3 possibilities when it comes to X equals B. There is a unique solution. There is no solution. And there are infinitely many solutions. Okay, because it turns out that if you can find 2 solutions that satisfy X equals B, in fact, you can automatically generate infinitely many solutions using just those 2. Okay, so that's why whenever you have a linear system, you either have one infinitely many or no. You don't have like 4 solutions. In a nonlinear system, you can have exactly 4 solutions, but not in the case of a linear system. Okay. Okay. I'm going to first simply state the conditions under which the different cases occur. Okay. We'll then look at geometrically what that means. Okay. But for now, we'll simply state it. We'll start with unique. Right. See, again, it's clear that whether or not this system of equation is solvable would depend on A and B. Right. So the conditions that we will state for these 3 possibilities essentially are conditions that depend on A and B. And they depend on this idea of a rank of a matrix. What is the rank of a matrix? We covered this, right? What is the rank? Yes, okay. That's the number of independent columns or rows. Good, okay. It depends on the rank. And it depends on this other concept, span of again, this is P cross Q, A Q. What is this? So essentially, this is span of the columns of A. What does that mean? Yes. What is span is essentially a set, right? What is it a set? What does that set contain? So sorry, number of, what is the P element? The number of vectors, is it? There are Q of them, right? You, right, right. Each of this is a P vector. You're right. Okay. But what is this set itself? So that's the set. This is a set of QP vectors. But what is the span of this set? Tell me. You said linear combination. That's correct. Linear combination of what? No. Okay. No. So this is essentially the set of all linear combination of the elements of this set. Okay. So which basically means what all elements or p vectors can I generate by simply taking the linear combination of these elements, the columns of A. Okay. We only need these two concepts. Okay. Now let's assume we're talking about a full rank matrix. What does full rank mean? When would you say a matrix is a full rank matrix? Right. Okay. Right. If it's n cross n, the rows and columns are independent. What if it's not square? When would you say that the it's a full rank matrix if it's rectangular? If you do you remember this, it is equal to the rank is always less than or equal to the smallest of these two numbers. If the rank of A is equal to the smallest of these two, then you say it's a full rank matrix. Okay. If you have a full rank matrix where that means if you have a square matrix that's full rank, then you always have a unique solution. Let me just add one more thing. So this is correct minimum of P comma Q. And let's say this is equal to P. Okay. So if P is equal to Q, you always have a unique solution. But when P is less than Q, then you have, so here you're talking about square full rank matrix. P. See, I've assumed the rank A to be P. That means these are the only two possibilities. It can either be square or a fat matrix. It cannot be tall because then P would be larger than Q. Then the rank cannot be P. Okay. Second one, you can still have full rank, but now the rank is Q. Okay. And now you can be less because you're dealing with a tall matrix. Here there are now two cases. Okay. If you have a tall matrix like this and you have a full rank matrix, now you the rank alone is not enough for you to know what will happen. This becomes important. If B belongs to if B is in the span, okay. So essentially we're saying if B is one of the linear combinations of if B can be generated as a linear combination of the columns of A, then you have a unique solution. Okay. And if B does not belong to span, then it's then there is no solution. This is when you have a full rank matrix. Full rank square matrix, always unique. Full rank wide or fat matrix, you have infinitely many solutions. If you have full rank tall matrix, then you have to now ask, is B in the span or not in the span? Okay. So it turns out if you have a full rank matrix, then all three possibilities can happen. Can either have unique, infinitely many, or no solution. Okay. What if the matrix is rank deficient? It's less than. Okay. Here, the moment the matrix is rank deficient, it turns out one possibility is out. Okay. The possibility of a unique solution no longer exists whenever you have a rank deficient matrix. Okay. There are only two possibilities now, either infinitely many solutions or no solution. And that is essentially, again, these two. So if B belongs to the span of the columns of A, then you have infinitely many solutions. If B does not belong to the span of A, then you have okay. It looks like there are too many conditions here. Okay. You can actually simplify this. Okay. And simplification only involves this. So you first ask, you only have to remember this. Okay. You first ask, is B is in the, sorry. Okay. You first ask this, is B in the span? Okay. If B is not in the span, so if the answer is no, then it's very clear. Right? Which makes sense, right? If you say X equals B, then what you're saying is the linear combination of the columns of A produces B. When you say B is not in the span of the columns of A, that means B cannot be expressed as a linear combination of the columns of A. That means there is no solution. There is no X that will give me B using the columns of A. If the answer is yes, yes, B does exist in the span of the columns of A, then there are two possibilities. If the rank of A equals the number of columns, or its full column rank, equals P cross Q, it's Q, then you have a unique solution. Rank of A is less than Q, and that's all. This contains this slightly more complicated enumeration of the different conditions. Okay. Is it clear? Okay. So we know that now there are these three possibilities, and whenever we can, so in general, you have these three possibilities, and let's assume that this can actually be solved. That means B is in the span of the columns of A. if that is the case, then the solution in general, let's say I write X star as a solution to this, has this form. You can write it like this. As a sum of two components, okay? The first one is called particular solution of Ax equals B. And this is called homogeneous solution of this equation Ax equals B. Okay. And the difference is this. Okay. And if you take this, right, if you take A, X star will actually give me B. And if you express X star like this, A XP plus XH equals B. And the property of the homogeneous solution is such that A into any homogeneous solution will always give me the zero vector. Okay, it's any vector from RQ such that if I multiply A by that vector, I get zero. And this is the zero vector from RP. Okay, if that is the case, then A into XP okay. It turns out that the homogeneous solution only depends on A. It does not depend on anything else. It does not depend on B. Okay, and of course your XP depends on A and B. Okay. And when X equals B has a unique solution, then your homogeneous. So if you when you have a unique solution, then your XH is simply equal to 0. Okay. XH is non-zero when you have a situation where Ax equals B has infinitely many solutions. Okay. I will leave it as an exercise for you guys. When you have infinitely many solutions, right? XH, there are infinitely many vectors, XH, that will actually give you AXH equals 0. Okay. The set of all homogeneous solutions to X equals B forms a subspace of RQ. This is for you to essentially demonstrate. You know what a subspace definition of a subspace is. You know what the set of homogeneous solutions are. Set of homogeneous solutions are essentially a set like this. Set of X such that A times X equals 0. This is the set of homogeneous solutions. Your goal is to show that this actually forms a subset of RQ because X's are from RQ. So this is a subset of RQ. Now we'll do a bunch of examples that have these different types of solutions and look at uh, the geometry of the solutions. Let's look at the first one. What is the solution to this problem? What is the solution? No. So now, what is the solution to this problem? No. How do you solve this? What is the set of linear equations corresponding to this Ax equals b? Can you tell me the two equations? Yeah. What is the first equation? Okay. 0. Second equation. Okay. What is the solution? 2 minus 1. Okay. Okay. That's correct. Now, so yeah. And let's do the column view. Right? The column view is, these are the two columns. This is A1, this is A2. A1 is like this. It's 1, 2, 1, 1. And then you have A2 is 2, 1. This is A1. This is A2. Right? And B is 0, 1. 0, 1 is here. So when you say the solution to this problem is 2 minus 1, that means you take 2 times A1, that's this. It's approximately here. Minus 1 times A2. Right? And if you add these two vectors, and if you draw the parallelogram, right, that will be this. Okay? You get B. That's the solution. Okay. This is your, this is your output space, right? This is your RP, right? Because B is from RP, and your columns aware are from RP. And in this particular case, this is essentially just R2. Your X, what space does your X come from? B is from RP. What space does X come from? If for general A, which is P cross Q, what is the size of X? Q, it's a Q vector, right? So that comes from RQ. In this particular case, P and Q are equal to 2. This essentially R2. So the solution to this particular problem, Ax equals 0, 1, is essentially this point 2 minus 1, 2, 1, 2 minus 1. That's this. This is your vector X star in RQ. RQ produces B, okay, under the mapping A. So A maps X star to, this is your A. Okay? So this point in your input space gets mapped to this point. Okay? Now similarly, you can ask, okay, if you can change this, you can ask, okay, what if this was 4, 5? Okay, so you do the same thing. There'll be some scaled version of A2, some scaled version of A1, and if you add them together, you'll get 4, 5. Okay, that will correspond to some point here, right? So when you have a unique solution like this, what you will find, what it means is this: every point here has a unique solution. That essentially means there is a single point in my input space that produces this point that I'm interested in, which is essentially Ax. Okay, and what about the homogeneous solution in this case? What are all the possible homogeneous solutions for this particular problem. Let's write that down. The set of all homogeneous solutions. What is a homogeneous solution from what we discussed earlier? Well, homogeneous solutions are the set of values of x that produce ax equals 0. In this case, the only value of x that will produce 0 is just this. Here, only 0 gets mapped to 0. No other element here gets mapped to 0. Okay? All right. That's the first case. Let's look at the second one. What is the solution in this case? What is the size of x here? Just for completion, let me just write p equals q equals 2 here. What is p here? What is p? Well, number of rows of the matrix A, that's 2. What about q? 1. Okay. So what can we say about the vector x? What space is it from? R1. R, it's a real number. Okay. So now the question is, okay, what real number when multiplied by this vector 1, 1 gives me minus 2, minus 2? Yes. What about the homogeneous solution? What real number, what set of real numbers x when multiplied by 1, 1 gives me the 0 vector? Only 0. There is nothing else you can put here that will give me the 0 vector. So again, well, in this case, it's not a vector, it's simply the. What is q? 2. Okay. So x comes from a two-dimensional space, and when you multiply it by a, it produces another vector from R2. Okay, this is your R2, RP, this is RQ. Where are the columns of A? Well, A1 is this. This is A1. A2 is minus 1, minus 1. That's this. A2. And the span of the columns of A is simply this. Where is B? Oh, I've flipped the colors, but that's okay. B is 3, 3. B is somewhere here. Now, what can you tell me about the solutions of this equation? What is x star? Is there a unique solution in this case? There is it? Okay. What is the unique solution? So 1, 2, 3. This is one of the possible solutions. Is what? 0. That will get mapped to B. Are there other points on this in this space R2 that will get mapped to this point? Well, the general solution for Ax equals B is a particular solution plus a homogeneous solution. So if you have any solution here, and if you simply add alpha alpha, right? For example, 3 0 works, right? If I add these two, 3 plus alpha and 0 plus alpha, and I put it back here, I'll still get 3 3. You can verify that. Okay. So in fact, if you choose any vector of this form, alpha alpha, and you add it to 3 0, that will also take me to B. Okay. In fact, what does the vector alpha set of all vectors alpha alpha look like? If I were to draw it in R2, yeah, it's this line. right? A set of all these points. In fact, this line is your set of homogeneous solutions. And you can already see it's a line passing through the origin. That means it has to be a subspace of RQ, okay, which you were supposed to show earlier that I had given as an assignment. But geometrically, you can see that it does form, at least in this case, it forms a subspace of R2, right? That means if you take any points here and you add this vector 3, 0, that will produce B. And what is the solution in this case? Without algebraically trying to solve it, can you, from the geometry, can you tell me if it has a solution? You're shaking your head. Does it mean no solution or you don't know? Yeah. Yes, it's not in the span of the columns of A, it's outside. That means you cannot get to this point by simply doing AX, because AX will only produce points along this line. Okay, so in this case, it does not have a solution. And you will see that this also fits into the previous picture, because B2 is not in the span of the columns of A. Then the first condition is satisfied, then there is no solution.